In my earlier video, I had discussed about Riemann integration and some property of Riemann integration, and I had seen how a function will be Riemann integrable. Today I will discuss this topic more elaborately. At first I will start with one example. First example, if f is defined on the closed interval 0b, where b greater than 0 by fx equal to x square, then at first we have to find the function f is Riemann integrable. Then we have to find the value of integration from 0 to b, because here function is defined on the interval 0b. Fx dx equal to b cube over 3. Here for this we have to find just LPF and UPF. Since here the interval closed 0b, at first we have to find the delta x, and delta x would be b minus 0 over n. That means this would be b over n. That implies length of every interval would be b over n here. Now we have to at first partition this interval 0b. Here the partition is look like x0 equal to 0, x1 would be b over n, x2 would be 2b over n, and up to xn minus 1 would be n minus 1 over b over n, and xn would be nb over n. Okay? That means this is the partition of the interval closed 0b, and consider the subinterval ik. Then in this subinterval, at first find the capital Mk and small mk. Since the function fx equal to x square, so if we consider this subinterval, so obviously the highest value exists at the end point. So mk would be kb over n whole square. That means, and this is equal to k square b square over n square, and small mk would be, obviously the infimum exists at the point k minus 1 over b minus n in this subinterval. Then this would be k minus 1 times b over n whole square. This is equal to obviously k minus 1 whole square times b square over n square. Now we have find the capital Mk and small mk, and now we have to find for Riemann integrable the UPF and LPF. And the value of UPF would be summation k equal to 1 to n capital Mk times delta xk. Just put the value. This would be k equal to 1 to n. Capital Mk means here k square b square over n square, and here delta xk means b over n. That means UPF would be b cube over n cube summation k equal to 1 to n k square. Okay? Here UPF, not k, and we all of us know this value I had studied this value in 12th standard. This is equal to b cube over n cube, and this value is n times n plus 1 times 2n plus 1 over 6. Okay, and this is equal to actually b cube times n plus 1 times 2n plus 1 over 6n square. Now similarly we have to find LPF. Here at first put the value small mk. This value would be k minus 1 whole square times b square over n square, and the value of del xk here, just put the value b over n. That means this is equal to actually b cube over n cube summation k equal to 1 to n k minus 1 whole square, and put the value similar to before. This value would be b cube over n cube. Here k, this value would be, since here k minus 1, that means this value would be n minus 1 times n times 2n minus 1 over 6. That means the value of LPF equal to b cube over n square times n minus 1 into 2n minus 1 over 6. Here I have find UPF and LPF. Now we have to find upper Riemann integrable and lower Riemann integrable. Then the value of lower integrable would be, we all of us know this is equal to supremum p belongs to closed interval 0ab in the set LPF, which is, we can write also limit n tends to infinity b cube over n square times n minus 1 times 2n minus 1 over 6. Okay, that means we have to find this limit. At first remove this part b cube over 6, then this would be limit n tends to infinity. For this limit, n squared times 1 minus 1 over n times 2 minus 1 over n over 6 n square. Sorry, here not 6. Here I have removed 6. That means this value would be b cube over 6. Cancel n square. Then this value of the limit would be 2. That means actual this value is equal to b cube over 3. Sorry, here I have forgotten to write the f dx. Here would be f dx. We have to find the upper integration 0 to p bar fx dx, which is equal to just we all of us know infimum of the set p belongs to closed 0b of the set UPF. And similar to before, just put the value and find the limit. Then this value would be b cube over 6 times 2, which is equal to actually b cube over 3. Since the value of upper lower integration and lower Riemann integration is same, which is equal to b cube over 3, that means our function f be Riemann integrable. Are you getting the method? Well, now I will prove the integrability of continuous and monotone function. And to prove the integrability of continuous and monotone function, I will here use this condition. If f is Riemann integrable if and only if given epsilon greater than 0, there exists a partition P such that distance between UPF minus LPF less than epsilon is actually greater than equal to 0. That means actually we have to find one partition such that the distance of UPF and LPF close to each other. And to prove this theorem, I will use this property. See, if a function is continuous on the closed interval AB, then that implies f is integrable. And the proof is such type. F is a continuous function on the closed interval AB, and since f is continuous function on the AB, implies f is always bounded function. And since f is continuous and bounded, that means obviously f is uniformly continuous. Since f is uniformly continuous, then for all epsilon greater than 0, there exists delta greater than 0 such that absolute value of f of x1 minus f of x2 strictly less than epsilon over v minus a. Since f is uniformly continuous, so this is true for all x1 and x2 belongs to closed AB, and absolute value of x1 minus x2 less than delta. If the function is Riemann integrable, consider a partition P which is actually a equal to x0 less than x1 less than x2, which is also less than xn equal to b, with the condition norm p less than delta. So if is continuous on the closed interval, consider here the subinterval xi minus 1 to xi, then obviously it has a maximum and minimum. Consider the function has a minimum at the point ai and the function has a supremum at the point bi. On the interval, here the subinterval xi minus 1 to xi. That means small mi equal to f of ai and capital Mi equal to f of bi. Since f is uniformly continuous, so this condition is true for all x1, x2 in the interval closed AB. Consider this relation as 1. Then this is also true for this subinterval xi minus 1 to xi. And then because this is the supremum and infimum value of the function, then this value would be capital Mi minus small mi, which is less than epsilon over b minus a. And this is true for all 1 to n. Now we have to find distance between the upper sum and lower sum. That means distance between UPF minus LPF, which is equal to summation I equal to 1 to n capital Mi del xi minus small mi del xi, and which is equal to actually capital summation I equal to 1 to n capital Mi minus small mi times delta xi. Now obviously from this equation we can write this value, since this value less than epsilon over b minus a, so put this value times delta xi, then this value would be, just remove this part from summation, then this value would be epsilon over b minus a times summation I equal to 1 to n del xi. And if we find the value of summation, then this would be epsilon over b minus a times xn minus x0, which is equal to, just put the value, xn would be b and x0 would be a. Then this value would be, this is also less than equal to, that means from this line we can tell this relation less than equal to epsilon. Therefore I have got distance between UPF minus LPF less than equal to epsilon. That implies f is obviously Riemann integrable on the function AB. Okay? Few minutes ago I had seen fx equal to x square is Riemann integrable on the closed interval 0b. Since fx equal to x squared is continuous function, so obviously this function would be Riemann integrable. Are you getting why this theorem is more important? Any continuous function will be Riemann integrable. The theorem, every monotone function will be integrable. Actually, every monotone function always integrable. It may be monotone increasing or monotone decreasing, but still it is Riemann integrable. For this proof, consider f is monotone increasing function. Suppose f is monotone increasing function, and I will prove this equation by UPF minus LPF less than epsilon by this condition. So, at first choose arbitrary epsilon greater than 0, then get n such that b minus a over n less than epsilon. Now consider a partition P such that del xi less than b minus a over n, and this is true for all I. Consider supremum of the function is capital Mi and infimum of the function is small mi, and here actually I have considered the subinterval xi minus 1. Then difference between UPF minus LPF equal to summation I equal to 1 to n capital Mi minus small mi times delta xi. Since the function is monotone increasing, so obviously in the right hand point the function has a maximum value, and in the left hand point the function has a minimum value. Since I have taken the partition as delta xi less than b minus a over n, so just put the value, then this would be less than equal to summation I equal to 1 to n capital Mi minus small mi b minus a over n, and just remove the part from the summation, then this would be less than equal to b minus a over n summation I equal to 1 to n capital Mi minus small mi. Now I will put the value. This would be less than equal to b minus a over n, and here I will write just as f of ai minus f of here f of xi minus f of xi minus 1. Calculate the all summation, then this value actually would be fb minus fa, and this value actually less than equal to b, because I have considered it b minus a over n less than epsilon. Are you getting why I have considered it? For prove the theorem. Then this value would be less than epsilon times fb minus f of a, but obviously would be less than epsilon. UPF minus LPF less than epsilon, so every monotonic function will be Riemann integrable. For example, consider f be a function on the closed interval 0, 1 by fx equal to 0 when the value of x not equal to half, and at the point half the value of the function is 1. Obviously this function has a jump discontinuity at the point half. So by the theorem we can tell easily f cannot be Riemann integrable on the closed interval 0, 1. Are you getting the idea of the theorem? Well, I will say one nice example. Here fx equal to x, where x belongs to q intersection of closed interval 0, 1, and x square when x belongs to q complement intersection closed interval 0, 1. Then find the upper sum and lower sum. Now we have to prove if f is Riemann integrable on the closed interval 0, 1. similar to, we have, before example we have to prove it. Here y equal to x line and this is the x square graph. To find the Riemann integrable, at first we have to partition close interval 0, 1. I have partition is as 0, 1 over n, 2 over n equal to n over n equal to n over n equal to 1. That means here delta x equal to 1 over n. Now we have to find capital Mr and small mr. Consider the sub-interval xk minus 1 to xk. And notice in this sub-interval maximum value at first. See the graph. Always maximum value exists at the function y equal to x. If you choose this sub-interval, if we consider this is xk minus 1 to xk, notice here always maximum value exists at the point xk and the function y equal to x line. That means we have to find capital Mk where x belongs to closed interval xk minus 1 to xk fx, and here in this interval supremum value exists at the, since at the line y equal to x, that means this value would be xk, which is actually equal to k over n. Now we have to find small mk, which is equal to infimum x belongs to close interval xk minus 1 to xk fx. Obviously all infimum exist on the function y equal to x square. That means small mk, which is infimum fx where x belongs to xk minus 1 to xk, this value would be infimum exists at the point xk minus 1 and here the function is x square, that means this value would be xk minus 1 whole square, and which is actually equal to k minus 1 whole square over n square. Are you getting? That means this is the capital Mk and this is the small mk. Now we have to find UPF and LPF, which is actually similar to summation k equal to 1 to n k over n times 1 over n, and this is actually equal to 1 over n square summation k equal to 1 to n k, and this value is similar to 1 over n square n into n plus 1 over 2. The value of LPF would be summation k equal to 1 to n small mk times delta xk, and this value actually equal to summation k equal to 1 to n k minus 1 whole square over n square times 1 over n, and this value is actually equal to 1 over n cube times summation k equal to 1 to n k minus 1 whole square. Are you getting? Value is actually similar to n minus 1 times n times 2n minus 1 over 6. Now we have to find the upper Riemann integrable and lower Riemann integrable. And to find upper Riemann integrable, one method which I have done few minutes ago, here we have to use the limit n tends to infinity, and similarly for lower Riemann integrable we have to find upper Riemann integration would be 0 to 1 bar fx dx, which is actually equal to 0 to 1 bar supremum of the function is x dx, and this value would be half, and which is actually similar to limit n tends to infinity UPNF. Are you getting these two methods? If you find the limit here, obviously this limit would be half. Similarly, lower Riemann integrable would be 0 bar to 1 fx dx, which is actually equal to 0 bar to 1 x square dx, whose value would be 1 over 3. And this is actually equal to limit n tends to infinity lower sum, that means LPNF. Here if we apply the limit, then this limit would be similar to 1 over 3. Are you getting how we have to find lower integrable and upper integrable? If this value is not same, so obviously f not be Riemann integrable on the closed interval 0, 1. Are you getting? I will say one example which had come CSR net to June 2016 exam. The question is, define f on the closed interval 0, 1 by fx equal to x square when x belongs to rational number and x cube when x belongs to irrational number. Then option 1, f is not Riemann integrable on the closed interval 0, 1. Option 2, f is Riemann integrable and upper Riemann integration is equal to 1/4. Option 3, f is Riemann integrable and lower Riemann integration is equal to 1/3. And option 4, 1/4 less than equal to integration 0 bar to 1 fx dx, which is less than equal to integration 0 to 1 bar fx dx, which is equal to 1/3. Where integration 0 bar to 1 fx dx less than equal to integration 0 to 1 bar fx dx, which are upper and lower integrable function of f. This question had similar type of question which I had defined few minutes ago. Similar type, fx equal to x and fx equal to x square in irrational number and irrational number, but here just function is different. Here this is the picture, this function is x cube and this is x square. Here since x square greater than x cube on the closed interval 0, 1, so here in each subinterval x square has maximum value and in each subinterval x cube has minimum value. Are you getting how we have to solve any question? Well, similar to before, option 1 is a right option. F is not Riemann integrable on the closed interval 0, 1. The lower integrable would be 0 bar to 1 fx dx would be, since x cube has a minimum in each subinterval closed interval 0, 1, that means this value would be 0 bar to 1 x cube dx, which is equal to 1 over 4. Means lower integral is equal to 1 over 4 and upper integral would be equal to 0 to 1 bar fx dx. X square has maximum in each subinterval of closed interval 0, 1. That means this is equal to 0 to 1 bar x square dx, which is actually same to 1/3. Are you getting? That means the value of upper integration is 1/3. So this option is wrong option and value of the lower integration is 1/4. So this option also wrong option. Here also it has indicated f is Riemann integrable. So obviously this is wrong because actually the function is not Riemann integrable. Fourth option indicate 1/4 less than equal to integration 0 bar to 1 fx dx less than equal to 0 integration 0 to 1 bar fx ds, which is equal to 1/3. This is also wrong option. That means only option 1 is a true option. Are you getting how we have to find Riemann integration of any function? Well,